As in the previous lecture, we discussed how a triode valve used to play the role of a constant current source to make it work as an amplifier. Now we'll see how a transistor plays the same role as a triode valve plays. A transistor is a three-layer device. That means one type of semiconductor is sandwiched between the other type of semiconductor. It may be, let's say, P and P, or it may be NPN. The transistor can be of two types. Either it can be P and P, where a thin layer of N-type semiconductor is sandwiched between two layers of P-type semiconductor, or it can be a NPN transistor, where a P-type semiconductor, thin layer of P-type semiconductor is sandwiched between two layers of N-type semiconductor. As I told you earlier, they have got three terminals. One is called emitter, it emits the charge carriers. There is base, which plays the role of grid, and then there is collector, which collects the charge carriers, which plays the role of a plate of a triode valve. Similarly over here, it has got emitter, base and collector. So it's a three-layer, three-terminal device. It's a three-layer, three-terminal device. Although emitter and collector are made up of same type of semiconductor. This is P-type semiconductor, this is also P-type semiconductor, or in an NPN transistor, both of them are of N-type semiconductor. But they are different. You cannot simply say that both P and this emitter and collector both have P-type semiconductors, so emitter can be replaced by collector and vice versa. No, you cannot do that because of two reasons. Number one, size. The size of emitter and collector is not same. Collector is made bigger than emitter. The size of collector is bigger than emitter, which is bigger than base. This is valid for both types of semiconductors. Collector is made bigger than emitter, and emitter is bigger than base. Base is very, very thin. Why collector is made bigger? As we'll see the working of a transistor, you will see that collector has got the role to collect all the charge carriers coming from emitter. And larger is the physical region of collector, there are more chances of collection of the incoming charge carriers. If an electron is coming and there are so many holes distributed across collector region, there are chances. If it's a collector is longer than emitter, there are chances that those electrons, while coming through the collector, may get neutralized by some of the holes. So collection efficiency of a collector will increase if it has got physically larger dimension. Secondly, during the working again, we'll see that all the electron hole neutralization, if not all, more than 95-98% of the electron hole neutralizations take place in the collector region. And as an electron hole neutralization takes place, some energy is emitted. You should understand this thing, that electron hole neutralization is nothing but de-excitation of an electron to a ground state or a valence band hole. That means that some energy would be emitted whenever an electron hole neutralization takes place. And that means that all the heat is being produced in the collector region. If collector is bigger in size, it will have larger surface area that will help it dissipating that heat which is being produced in the collector. So collector is bigger in size than emitter because of two reasons. Number one, it increases its collection efficiency, charge carrier collection efficiency, and it helps in dissipating the heat produced in it due to electron hole neutralization. And there is another reason, you cannot interchange the emitter and collector. The doping of emitter is larger than collector. As far as doping level is considered, emitter has got higher doping level than collector, which has got higher doping level than base. As the name is suggesting, emitter need to emit charge carriers. That's why its doping level is made high. And we don't want too many charge carriers to be lost to the base region. That's why the doping of the base region is made very, very low. Now let's see. Okay. Now, Let's see how a transistor works. I give you two golden rules. Two golden rules are that emitter junction is always forward biased because it needs to push the charge carriers, and collector junction is always reverse biased. It will have an opposite polarity to attract these incoming electrons from the electron or any other charge carrier, electrons or holes, to the it will try to attract those in the collector region. Let's see how a transistor works. But before a transistor works, we must understand that a transistor, whenever we wish to use it as a two-port network. If I wish to use a transistor as two-port network, that means some signal will be coming from input and I'll be getting the signal output from the output port. So they have got input port and output port, and obviously you have got two terminals for input and two terminals for output. You need four terminals, but a transistor has got only three terminals, so one terminal is made common both to input as well as output. Therefore, transistor can be operated in two different modes. One is called common base configuration and the other is called common emitter configuration. Common collector has got certain issues as emitter follow something that we'll discuss in a separate lecture. But transistor mostly is used either in common base configuration. This mode of operation is that the base is connected to both input terminal as well as to the output terminal, and it may also be used in common emitter configuration, where the emitter junction, terminal would be made common to both input and output. So let's start with the working, and two golden rules. One is emitter base junction should always be forward biased, collector base junction should always be reverse biased. Let's proceed with it. This is emitter, this is base, this is collector. I am say using PNP transistor. Things would not be much different when I will be using NPN transistor, except the charge carriers. Charge carrier polarity will change. I have kept this space open. How to connect a battery over here? This is P and emitter, this is base and N. So this is a emitter base junction, this is emitter base junction, and it should be forward biased. So for forward biasing, P is connected to positive and N is connected to negative. Normally, by convention, this battery is termed as VEE battery. Let's say this is variable in nature. And collector base junction should be reverse biased. So P should be connected to negative and N should be connected to positive. You can see the base is connected to both input as well as output. That's why you may see that it is a common base kind of configuration. It would not be exactly right to call it common base configuration till I exactly draw the circuit diagrams. This is a basic crude form to understand the working of a transistor, but okay. Doesn't matter. Now, think of it. This battery is also variable and normally called VCC battery. Let's think of a kind of story over here. Let's say this is emitter and this is P-type semiconductor. Emitter is highly doped, so it has got large number of holes over here. Say there are 100 holes, just for the sake of an example. Let's say there are 100 holes. Now these 100 holes are being pushed by the positive terminal of VE battery across the junction. Now there is a potential barrier existing across the junction. If it's a silicon transistor, it will be of the order of, even if it's a germanium, it's of the order of 1 electron volt. So when this voltage is sufficient to push these holes across this junction to cross over that barrier, these holes reach this base region. But remember, base region is very, very thin physically, and further it is very lightly doped. It is very lightly doped. So there are not enough electrons in the base region to neutralize these 100 holes. Only 2 to 5% of them get neutralized, and remaining under the repulsion of this force and under the attraction of this negative terminal of VCC battery reach the collector region. You can think of the situation as if, let's say, there is a mass meeting going on. Some politician or someone is conducting a function. He is addressing people, and there are large number of people sitting on these two sides. And there is a small central corridor kept open. There are only different kind of people. Let's say they are popes. They are moving around in the central region. The people over here and people over here are same, but the people in the central region are different. They are policemen. Now, let's say something happened, and the people in this region were pushed across to this region. There was something of attraction over here, and over here they were being pushed across this central corridor. What will happen? As they try to cross over, the policemen try to stop them. They just hold on to them. But since there are not enough policemen, they cannot hold on to all those 100 people who are over here. So what will happen? Only 2 or 3 people would be caught by these policemen, and remaining will cross over to the next region. As these policemen are holding on to these people, now they are immobile because they cannot catch anyone else. If they want to catch anyone else, they will leave the first person and catch the other one else. They will by no way help them in keeping the discipline. So what happens? They ask for more policemen. So if 2 policemen are neutralized in this region, the central force sends in 2 more policemen. But by that time, most of these 98 remaining people over here, they have crossed over to the other region. The same thing is happening over here. Think of this. This positive is pushing these holes across this region. The central region has got electrons. They don't want these holes to go to the other region. They try to stop them rather. They are holding on to them. They have neutralized them. But since their number is very less, why their number is very less? Because the base is thin physically and it has got low doping level. So most of the holes will cross over to the collector region. But since 2 electrons get neutralized in the base region, these 2 electrons, this deficiency of 2 electrons would be compensated by the negative of the battery. So 2 electrons go from this region, and remaining 98 holes reach the collector region. You should understand this thing that if electrons are going in this way, the conventional current would be in this direction. And this is what we call as base current. And you should understand right over here that base current is quite small in comparison to emitter current. Emitter current was because of 100 holes, 100 charge carriers, but the base current is only because of 2 charge carriers. So base current is quite small in comparison to emitter current. Typically, emitter current is of the order of a few milliamperes, whereas base current is of the order of a few microamperes. As the holes now reach the collector region, what happens there? It is already a p-type semiconductor. It has got its own holes. Now 98 holes have also come from this side. So this makes holes surplus in the collector region. There are so many vacancies over there. So what happens? That these vacancies attract electrons from the negative battery of this negative terminal of battery VCC. These 98 vacancies are filled by 98 electrons supplied by the negative of collector, negative of VCC battery or collector battery. Now think of it. There were 100 holes. So emitter current is because of 100 charge carriers, base current is because of 2 charge carriers, and the collector current is because of 98 charge carriers. Or you may say 2% and 98% the same way. Now what happens? As these electrons are neutralized in base region or in collector region, to which region actually these holes belonged to? These holes belong to emitter region. So for every neutralization which is taking place in base region or in collector region, a new covalent bond breaks in the emitter region. Now you may say, why a covalent bond breaks? Here, when we say covalent bond breaks, this is so it should be slightly differently interpreted from the way you interpret it in chemistry. We are not talking about that kind of bond breaking. It is almost same thing, but basically we are over here trying to say that an electron goes to connection band. An electron goes to connection band. If an electron goes to connection band, what happens? An electron and a hole is generated. So whenever a covalent bond breaks, an electron hole pair is generated. Now, so 100 electrons and 100 holes have generated in emitter region because 2 neutralizations took place in base region and 98 neutralizations took place in collector region. So total 100 neutralizations have taken place. So 100 new covalent bonds break in the emitter region, and what happens? These 100 holes are again pushed by this positive of VE battery across the junction, and 98 electrons, sorry, 100 electrons, they are attracted by positive of VE battery. The process again starts afresh. So in general, you may say that emitter current is equal to base current plus collector current, but at the same time, we should understand that emitter current and base current are almost same. And base current is quite small in comparison to the emitter and collector current. Now, how this behavior can be understood and why this thing is same as we did in case of a triode wall. The output current, if you have gone through the previous lecture, you must understand this time, that for making the amplifier, what I need a constant current source where the load resistance is not affecting the incoming current. Now let's see, I can do that by drawing the characteristics of a transistor. Let's draw it. And see, this is the symbol for a transistor. If the arrow is made towards the base, this is a PNP transistor. If arrow is outward like this becomes an NPN transistor. This is a PNP transistor. This side, which has got arrow, is emitter. The other tilted side is collector. This central side is base. To measure current, I am putting a milliamp ammeter over here, and this will measure emitter current. I am keeping the space for battery open. To measure collector current, I have put again a milliammeter over here, and again space for battery I have kept open. I will connect a voltmeter over here, another voltmeter over here. This will measure the voltage between emitter and base across emitter and base. So this is called VEB. This will be called VCB between the collector and base. How the battery should be connected. Since it's a PNP transistor, this is emitter and it has to be emitter base junction has to be forward wise. So P is connected to positive. This is VEE, and collector base junction should be reverse wise, so P is connected to negative. This is VCC battery. So this is the basic circuit to draw the characteristics of a transistor. Let us keep emitter current constant. Let's say I keep it at 10 milliamperes, and I draw a curve between the collector base and the collector current, collector base voltage and collector current. What would you get? These are called output characteristics, and this is actually the crux of working of a transistor. Along x-axis I am plotting VCB, and along y-axis I am plotting IC. Think of it. Let's say I haven't put any voltage over there and I've short circuited this VCC battery. There is zero voltage. VCB is zero. I've short circuited you shouldn't say that I have short circuited VCC, rather you should say I have short circuited collector and base, assuming that ammeter has got zero resistance. I have short circuited them. What will happen? If 100 charge carriers have started their journey, some of them got neutralized in the base region, remaining will reach the collector region. That may be 70%, 80%, but some charge carriers will definitely reach the collector region, and collector current would not be zero even if collector base voltage is zero. That means somewhere over here. Let's say 100 milliampere was sent from this thing, 10 milliampere was sent from the emitter, 6 milliampere, 7 milliampere, 8 milliampere, 8.5 milliampere would still reach the collector. So the current would not, IC would not be zero even if VCB is zero. Now you start increasing this voltage slightly. Now this is providing negative potential over here, which will be attracting the holes from the collector region to the attracting the holes coming from emitter region to collector region. Now what will happen? More of them will reach the collector. So current will, as you apply a slight negative voltage over here, the current will increase. Now what is happening? 100 started their journey, 2 were neutralized in the base region, remaining 98 have already reached the collector region. Now even if you keep on increasing the voltage at the collector, that doesn't affect, because all the remaining 98 holes have already come to the collector region. So by increasing the voltage, you won't be able to increase the collector current, and collector current becomes constant. Collector current becomes constant. Let's say this was when emitter current is 10 milliampere. You can increase the collector current only by doing one thing, by sending in more charge carriers from emitter itself. That means, let's say if emitter current is made 20 milliampere, then if initially there were 6 milliampere reaching over there, when 10 milliampere was the emitter current, if the emitter current is made 20 milliampere, now 12 milliampere will reach, current will increase and become constant like that. Don't think of these graphs as mere graphs. These graphs have revolutionized the electronics, the solid state physics, your life, and everything else around you has changed in last 60-70 years. Why? Look at this part of the curves. The current is constant, irrespective of output voltage. This is acting as a constant current source, as a triode valve was doing. So these curves show that a transistor can be used as an amplifier. And if you increase the emitter current further, you can get a graph like this. What will happen if I reverse the polarity of the VCC battery? Rather than attracting those holes, it will be repelling those holes, and current would suddenly fall down to zero. So this is a complete set of graph. Now in this region the current starts to increase very rapidly. If you are coming from that side, you may say it's falling. If you are going from this side, you may say that current is rising sharply. In this region, the current is rising sharply. This region is called saturation region, because in this region, what you did actually, you changed the polarity of the battery. That means now the collector base junction has also been made forward bias. Now both the junctions are being made forward bias. If both junctions are forward bias, it is very easy for current to flow from emitter to collector, and current suddenly increases. There is no resistance across the junctions, and hence in this region transistor acts as if it is an on switch. It is an on switch. If this is, let's say, 0, and if you go in this region where both the junctions are reverse bias, there will be hardly any current flowing through that. That is called cut-off region of the output characteristics. And this central region, where constant current is flowing, emitter junction is forward bias, collector junction is reverse bias. That's the region where transistor can be used as an amplifier, and that's what we call as active region. But what about the input characteristics? If you keep the output voltage constant and draw a graph between emitter current and base current, emitter current and VEB, base emitter voltage, what sort of graph you would get? Let's say collector is kept open now. Let's say collector is kept open. So this is acting just like a PN junction now. What will happen? The graphs are something like this. So this is emitter current. This is VEB. This is more like the working of a forward bias PN junction diode. But if you, rather than opening it, provide a negative voltage, the current will rise a little early. Let's say VCB was kept 0 and VCB is kept -1. So current will rise slightly early. This is what we call as input characteristics of a transistor. These are called output characteristics of a transistor. How this helps in its use as an amplifier, that I will discuss in the next lecture.